Welcome to the Chemistry, Biology and Math Revision Hub. Today we are doing the Pearson Edexcel International A Level Chemistry Unit 6 for June 2022. This is the Part 2 video of this paper. I will put the link to the Part 1 video below the description box. Let's begin with question 3. It says, brass is an alloy of copper. The percentage by mass of copper in a sample of brass can be determined by a three-stage process. Stage 1, there is oxidation of the copper to copper 2 ions with excess concentrated nitric acid. Remember, they are using excess to ensure that all the copper is oxidized. In stage 2, there is reduction of copper 2 ions to copper 1 ions with excess iodide ions. And then in stage 3, there is titration of the iodine produced in stage 2 against the standard solution of sodium thiosulfate. So they say in stage 1, 2.53 grams of brass is carefully warmed with 25 centimeters cubed of concentrated nitric acid in a 250 centimeter cubed beaker. The equation for the oxidation of copper metal by nitric acid is as shown below. So we can see this equation and the products. Then they say, state 2 hazards in this experiment, giving the precautions you would take to minimize the risk associated with each hazard. Assume safety spectacles and a laboratory coat are worn. When we look at this experiment, you can see they have worked with concentrated nitric acid. It is going to be highly corrosive, so they have to be able to wear gloves. And then there is this gas here that is very toxic. So here we can see NO2, or you could say nitrogen dioxide, is very corrosive. It is toxic, so they have to work or do the experiment in a fume cupboard. So I said carry out the experiment in a fume cupboard because a nitrogen dioxide gas is corrosive and toxic, and wear gloves because nitric acid is corrosive as well. Then here they say, state what would be seen during this reaction. I want us to go back to this equation. When you look at the observation, we see that this product here is a gas, and this gas is brown in color. So brown fumes are going to be observed during the experiment. Also, we can see that there is copper that is formed. Copper 2 is blue in color. However, in this experiment, they used excess concentrated nitric acid. So it means after the oxidation of all the copper, there is going to be some nitrate ions left in the solution that could interact with copper to create a green-like color. So there is a transition between blue and green. So you would say either a green solution or blue-green solution. Here I give the reason as to why. So for those of you who want to see how this experiment is carried out, this is the link to the YouTube video. Somebody did an experiment with this, and the colors are well observed in this video. So you can go onto there and try to observe what happens. Moving on. They say excess nitric acid must be neutralized before the iodide ions are added in stage 2. And they say sodium carbonate solution is slowly added to the cooled solution, and the solution is neutralized when a faint precipitate appears. Suggest why the solution is cooled before the addition of a sodium carbonate solution. Now we know sodium carbonate, and if you react sodium carbonate, when it reacts with nitric acid, of course, we're going to produce salt, carbon dioxide, and water. And carbon dioxide gas is going to be, there is effervescence of carbon dioxide gas. Now, if the nitric acid is hard, it means the reaction is going to be excessively fast or very vigorous, meaning there will be excessive effervescence of carbon dioxide gas. To prevent that, we cool down the acid first so that the rate of reaction will not be as fast or as vigorous. That is the reason why. Then next, ethanoic acid solution is added drop by drop to the neutralized mixture until the precipitate dissolves or redissolves. They want you to describe how the solution in the beaker should then be made into 250 centimeters cubed of a homogeneous solution before stage 2. This is preparation of a standard solution. So all you had to do is transfer the contents from the beaker and the washings. You have to include the washings. Washings are after you transfer the contents, then you add some little water into the container that contained the solution that you have transferred, rinse and pour into the volumetric flask, and then wash again and pour until you are sure that there is no remaining content or no remaining solution, so that the concentration is going to be as you calculated it to be. So we transfer the contents from the beaker and the washings into a 250 centimeter cubed volumetric flask. Then we will use the ionized water, or you could say distilled water, to add to the volumetric flask until the 250 centimeter cubed mark. Then we have to mix thoroughly to ensure there is a uniform concentration of the solution. So moving on. Here they say, in stage 2, 25 centimeter cube portions of the solution in stage 1 are transferred into conical flasks. 10 centimeter cubed of a solution of potassium iodide is added to each flask, and the mixtures are swirled. Copper 1 iodide is precipitated. The redox reaction for the reaction between, or a redox equation for the reaction between copper 2 ions and iodide ions is shown, as we can see here. They say the standard electrode potential for the half equation are as we can see here. Then they say use the electrode potential data to explain why the redox reaction might not be expected to be feasible. So the reaction should be copper 2 giving us copper 1. So you have to rearrange this to give us that. Remember, this should be a product. So you could change this equation. Let this be this side and the other side if you're combining the two. Or you could just leave it as it is. We know that the E for the cell, or the electrode potential for the cell, should be the electrode potential for the reduction minus the electrode potential for the oxidation. So in this case, it should be that minus that. So here we can see we are going to get this one here, reduction minus oxidation, which is 0.15 minus 0.54. And we can see here we get a negative 0.39 volts. This shows you that because of this negative, the reaction is not going to be feasible, because for feasibility to be established, it has to be a positive sign. Since it's a negative sign, that is why it's not expected to be feasible. Again, it should be reduction, which is that, minus the oxidation, and then it will give us negative 0.39 volts. Moving on, they say explain why the redox reaction does in fact take place. Now, despite the idea that we see a negative 0.39 volts, why does this reaction take place? I want to explain this using this information here. Now, keep in mind that I have flipped this equation to ensure that I satisfy whatever is required here. If this is going to be like that, I'm going to change this equation to make iodide to be at the reactant side and iodine and the electrons to be the product side, and then I combine the two equations to create something that would look like that. Of course, keeping in mind that you would have multiplied by 2 to ensure that everything is well multiplied through. So here what I said, combining, and again, I'm not sure if I multiply this by 2. I think this one should be iodide. Let me go back here and see. This is 2 to multiply through by 2. Yep, it's by 2 to make the electrons to be equal. That's what I did. And then I wrote the overall equation, which is that here. When I write the overall equation, I can see that we have the copper at the reactant side, copper ions, iodide at the reactant side, and then copper 1 at the product side, and iodine at the product side. Now, you remember during this experiment, they said that the copper 1 formed was removed. I want to take you back to show you where they said that. Just a minute, let me take you back. Where they say the copper 1 was removed. Here, reduction of copper 2 into copper 1 with excess iodide ions. And then here they went on to say titration with that in stage 2 against. Let me look a minute. I should be stage 2. Stage 2. They say excess nitric acid must be neutralized before the iodide ions are added in stage 2. And then they go on. There is somewhere they said where they removed the excess copper 1. Give me a minute. I'm checking it. Okay. Let me see. Mixtures. The redox equation is like that. If you go through some of these notes, there is somewhere they've mentioned that the copper 1 ions were removed. They removed the copper 1 ions, or the precipitate was removed before the next step was carried out. Please look through carefully. They talked about that. So removing of these copper 1 ions, it means the number of moles of some of these products is going to be reduced, and therefore equilibrium is going to be shifted to the other side. So shifting equilibrium to the other side ensures that this reaction occurs even if it was not expected to occur. Remember, copper 1, or the product that we're going to have in copper 1, is going to be precipitated and is going to be removed, and removing that ensures equilibrium is shifted to the right. So I said removal of copper 1 iodide, which is the precipitate, from the equilibrium causes the equilibrium to shift to the right. I just used this as an example. You're not required to write this on the exam question, or there are no marks awarded for this, but this tries to explain what is occurring here. So let's continue. Here they say the procedure in stage 3 is shown. The iodide produced in each flask from stage 2 is titrated with 0.095 mol per decimeter cubed sodium thiosulfate solution until the iodine color is pale yellow. A few drops of starch indicator are added. The sodium thiosulfate is added drop by drop with swirling until the end point is reached, and the titration is repeated until concordant results are obtained. They ask, give a possible reason why the starch indicator is added when the iodine color is pale yellow rather than at the start of the titration. The reason for this is they are trying to prevent the formation of an insoluble starch-iodine complex. If there is a lot of iodine and you add the starch, it means the starch and iodine are going to bind onto each other, creating something that is insoluble. The iodine will be removed from the solution and it's going to be kind of precipitated out. It means the reaction is going to be hindered because it will be as if there was less iodine in the liquid. So another part says give the color change at the end point of the titration. The color change here should be blue, black to colorless. The results of the titration are shown. So we see there is a Titer 1, Titer 2, and Titer 3. And here they say the final butyrate rating. So basically they've given us the information, final butyrate rating, initial butyrate rating, and then the Titer value. So they wanted us to find this. It should be 27.45 minus 1.00, which gives us 26.45. Here they say complete the table and calculate the mean titer of the concordant results. So concordant results should be within plus or minus 0.2. So when you check that and that, these two are not concordant. That and that are not concordant. It's only these two that are concordant because the difference is kind of very small. So I took this to be that, and I used them to calculate the mean titer. So that plus that divided by 2 gave me a mean titer of 26.55 centimeters cubed. And then they go on to say the redox equation for the reaction between copper 2 ions and iodide ions is shown below. So this is it. And they said the reaction of sodium thiosulfate solution with iodine is shown. That is another reaction. And they want you to calculate the percentage by mass of copper in the 2.53 grams of brass. They've given you the AR for copper, which is 63.5. So with this, since this is the one they used to titrate, it was coming from the butyrate and they gave us its concentration. We have calculated its Titer volume. We need to be able to use that to find the number of moles. So number of moles should be concentration times volume. This is the concentration, that is the volume divided by 1000 to convert it to decimeters cubed. And I get this as the number of moles. Now these moles are in the 26.55 of the thiosulfate that has reacted. However, when you use this equation, the ratio to thiosulfate to iodine is 2 to 1. And the ratio of iodine, this side, to copper is as well 2 to 1. So you can see this is 1 to 2, this is 2 to 1. It tells you the number of moles of thiosulfate are exactly equal to the number of moles of copper. I want to do this one more time. So here to find the number of moles of this are going to be a half times the number of moles of thiosulfate. So which is exactly this, a half times the number of moles of thiosulfate, 3 to minus. And the ratio here is 1 to 2. We can see this is going to be twice times a half times S2 or 3 to minus. So this gives us a 1. So it means the number of moles of these are exactly the same as the number of moles of that. So I skipped out some of those steps because when unnecessary, I just went straight to moles of copper in the 25 centimeters cubed because that is the volume that was used in the conical flask. So the moles of thiosulfate here are equal to the number of moles of copper in the 25 centimeters cubed, which are exactly that. So since I know the number of moles of copper, I can be able to find the number of moles of copper in the 250. This is in 25, multiply it by 10 to get the number of moles in the 250. And then knowing the number of moles in the 250, and they've given me the AR, or atomic mass, I can be able to find the real mass. So mass is equal to number of moles times, you could say MR, or I could call it the AR because this is just an atom, atomic mass of course of copper. So when I calculated that, I got 1.60163, as you can see here. That is the mass of copper in the brass. Now to find the percentage by mass, it's mass of copper in the brass divided by total mass of brass times 100, and it gave me 63.3054. Rounding it off, I got 63.3%. Let's continue. Here they say nitric acid reacts with iodide ions to form iodine. In another experiment, the nitric acid was not neutralized before the start of stage 2. Explain the effect on the value obtained for the percentage of copper, so here in the sample. Now remember, if you leave nitric acid in, since they've told us nitric acid reacts with iodide ions to form iodine, I want to take you back here. We will see that even as this experiment is being carried out, the iodide formed is going to be broken back into iodine. And that means every iodine, or at the beginning, as long as we still have the nitric acid in this solution, iodine that is going to be present is going to be, iodide that is going to be present is going to be converted back to iodine, and this reaction will require more thiosulfate. So thinking about that, we'll see that leaving nitric acid in the flask will lead to formation of more iodine. I said even the produced iodide could be converted back into iodine, and so the volume of thiosulfate used would be greater and more moles of copper calculated, leading to a higher percentage of the copper calculation. So in this case, you'll see you'll require more thiosulfate, and then you would predict a higher number of moles of copper, and therefore a higher mass of copper present, and the percentage by mass would be a little bit higher. So this brings us to the end of question 3. Let's go to question 4. Question 4. Limonene is a liquid hydrocarbon which has a boiling temperature of 176 degrees Celsius and a density of 0.851 gram per centimeter cubed. It can be obtained from orange peel using steam distillation. The distillation apparatus is shown. Here we can see steam distillation setup. Here we have the water being heated into steam, and then the steam evaporated. It goes into here where the mixture is, and then the evaporation will occur into the condenser. So they say, label the diagram to show the direction of water flow in the condenser. Within this condenser, cold water is going to move into the condenser at this point, so the arrow should be pointing upwards. And then the water that has been used to cool is going to move out here, so we can see water coming out at that point here. Then next they say, give a reason for using steam distillation to extract limonene. Steam distillation prevents decomposition of substances whose boiling temperature is a little bit higher, so when they use steam distillation, they will evaporate or come off at a temperature below their boiling point, and that will ensure that decomposition is prevented. So moving on here, they say the distillate may be collected in a pear-shaped flask. Complete a label diagram showing the distillate. You should show clearly the limonene layer. If you look at the beginning of the question, the limonene has a density of 0.851 gram per centimeter cubed. Here the density of water is 1 gram per centimeter cubed. I'm considering pure water. So pure water should be heavier than limonene, and therefore limonene is going to be found at the top of, or in the top layer of the two. So it should be at the top and water at the bottom. The next they say limonene exists as optical isomers. Identify the chiral carbon on the diagram. So when we see here, I drew out all the carbons. You can see that all the other carbons have at least 2 more groups that are similar attached to them, or at least there is a carbon-carbon double bond around them, so that means they cannot be chiral centers. This is out, that is out, because there is a carbon-carbon double bond. That is out, that is out, that is out, 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 and out, except this one. So this one is the only chiral center present. The next part says the limonene extracted from orange peel is D-limonene. Show how the presence of a single optical isomer could be confirmed, naming the apparatus used. No experimental details are required. If an experiment is carried out and you produce an optical isomer, there is a possibility of a racemate mixture being formed, whereby even if they're optical isomers, overall there will be no rotational plane polarized light. However, in this case, if they say a single optical isomer is produced, it means plane polarized light should be rotated by this isomer. Therefore, we use a polarimeter. And if plane polarized light is rotated, then it is a single optical isomer. So this one here can be used to confirm if it's a single optical isomer. Moving on, a student obtained 1.20 centimeters cubed of limonene. Calculate the amount in moles of limonene produced. So we were given the density previously as 0.851, and we have the volume given 1.2 centimeters cubed. So we can find the mass, which is density times volume. Substituting the values, we get 1.0212 grams. And now we are going to go to find the molar mass of limonene. Let me take you back here. You can see from here, from the structure that we were given, the molecular mass is carbon 10, hydrogen 16. So we can use this to calculate the molar mass. I'll take you back. Here we can see that the molar mass is going to be 136 gram per mole, if you can see how I calculated that. Now we can find the mole since we have the mass and we have the molar mass. Dividing the mass with the molar mass, we get 7.5 times 10 power negative 3 mole. So the next part, they say limonene reacts with acidified potassium manganate 7. give the color change for this reaction. When you look at the structure of limonene, we saw there were carbon-carbon double bonds, so it means when they react with potassium manganate 7, they will form diols as the purple color turns to colorless due to that. So the color change should be purple to colorless. Down here they say, draw the structure of the organic product which might be expected when excess acidified potassium manganate 7 reacts with limonene. If they use excess, it means all the carbon-carbon double bonds were substituted for. So I drew here the structure of limonene and how it would be if the OH or the diols were produced. So this carbon-carbon double bond will be broken, and then around each carbon, an OH bond will be attached. Also here we can see this double bond will be broken, an OH attached to this carbon and an OH at that carbon. So we can see a diol will be produced here and a diol will be produced here, as we can see. So this is the structure that will be produced after the double bonds have been broken and the oxygen hydrogens are attached onto the carbon, which was previously part of the carbon-carbon double bond. So this brings us to the end of this question, as well as the end of this video, as well as the end of this paper. Thank you so much for being with us. Please do not forget to subscribe. See you in the next video. Bye-bye.